Let's see. So what we're going to do now is switch to, do I have to do this? Is this required to give for something? I don't know. So we're switching to rotational motion. So let's look at our new list of concepts here. Is it becoming funny? I don't know. Okay, here we go. So our new things we got to think about here. Uh-oh. This used to work this way. Here we go. I'm telling you, we're doing this poster thing. I don't care what it takes. If I have to hold it up, here we go. The holder is broken. We're going to talk about the kinematics of circular motion. Okay, that's basically what we're going to talk about. And let me just read from it. We're going to talk about the kinematics of circular motion. This is like notes for me in 10 years. This is how I'll lecture. So the kinematics of circular motion, the dynamics of circular motion. And you know the difference. Kinematics is how you describe motion, and dynamics is the force that causes that motion. So we'll talk about centripetal forces. That's going to be today, and then Thursday will be gravity, and how gravity causes circular motion. So if you look at the schedule of topics, you can see we're sort of covering a huge range and jumping all over the book, because we're sort of contracting a lot of things down. But we're giving you the critical important parts. Okay? Here we go. So let's talk about that now and get rid of this. Here. Oh, that was that one, of course. Yes, circular motion. And that is for later. Okay. Let's get rid of all this. Okay, so here we go. So normally, we would cover this longer. Can you put up the chart so I can take a picture of it? You can take a picture of it after. Normally, we might point out that we would cover these over a month. And I would be pointing out very carefully the exact differences between these things. And I'm still going to tell you, we're just not going to harp on it for like a week, okay? Or for weeks. So angular, circular, rotational kinematics. So underneath, I'm just going to put in parentheses, subtle differences. They're not exactly the same thing, but they use very similar mathematical symbols and concepts, okay? So in this class, we're going to do this for 2 weeks. So we're going to kind of blend them together a little bit, but I'll point out when we're getting to parts where they're kind of different. So the simple difference is we are turning rather, than translating. So all the kinematics we've done so far has been something translating in x, maybe both x and y, which makes a parabola. That's pretty much what we've done. So now we're going to actually turn things. So here is our wheel here, and here it is turning, and say this is the horizontal, like this is theta equals 0, so it's going to go like this, right? It's going to turn around and around. It's not translating anywhere. It's just rotating about a certain point. Okay, so let's draw that like that. My circles are better than Costanza's circles. And here is 0 degrees, right? And let's imagine this is just some edge point on that circle. Or this could be a wire and a bead is going around the wire. And for now, let's just say it goes in any old crazy kind of motion. We just want to talk about kinematics and how we're going to describe that motion. Well, that's what kinematics is, right? So we're going to talk about 3 parameters that you may sound familiar. The angular position. Before we had the position x. Now we have the angular position. Usually you can call it theta relative to wherever the origin is. Theta equals 0. Right? So if that's theta equals 0, then this is some angle theta from the center like that. So there's theta. So that's like position x. Theta, that. The units are in degrees or radians. Oh, we're going to talk about radians today. Hopefully you love radians already. 2 is angular velocity. So just like position, or just like something moving along, it can go through different distances in a certain time. This can go around different amounts in a certain time, right? And that is how fast around it's going, would be the simple definition, and we call it omega, right? The Greek letter omega, and it's equal to just d theta dt. So it's just like the other kinematics. Just like v is dx dt, omega is the equivalent d theta dt in, you can guess, radians per second. Okay. So in some problems, like when you're setting up a problem and talking about the angles, you'll often see it in degrees, but then when you go calculating something in omegas, it'll always usually be in radians. You rarely see degrees per second. So I can't claim we should always do radians or we should always do degrees. It gets very mixed up. So you just got to be good at going back and forth. So I bet you guys could think of the third one, right? Angular acceleration. So I'm not even going to define it. You know what it is. It's the time derivative of angular velocity. It's how fast the velocity changes. It is alpha. This is not the centripetal acceleration. We'll get to that later. This is the actual angular acceleration. Let's see, angular acceleration. It's d omega dt in radians per second squared. So there's the basics. So now we could spend a week saying, well, theta is theta I plus omega naught t plus 1/2 I alpha t squared. And omega final squared equals omega initial squared plus 2 alpha theta, right? So all those kinematics equations from translation copy over exactly to rotation. So we could spend a whole week on rotational kinematics, but we don't want to. It's boring. It's the same thing, just something going round and round. So what we're going to do is move on to more interesting things here. Get on with our lives. But I mostly just put that just to get the basic parameters in front of you. Angle, omega, and alpha are the rotational versions. Okay.